Superconductors. Now we talked about a lot of different metals, and we talked about the fact that they have a finite resistance. The resistivity goes up as the temperature goes up. The resistance goes up as the temperature goes up. But there's an actual class of material known as a superconductor, which has no resistance at all. And these are really remarkable materials because they seem to defy nature. A superconductor actually has no resistance based solely on a quantum mechanical phenomena. Basically what happens is electrons are what are called fermions. No two electrons can occupy the same energy level. When we have a superconductor, two electrons pair up to go from a fermion to what's called a boson, or basically they go from a half spin to a spin zero. And when they make that transition, all the electrons can have the same energy, and the de Broglie wavelength of the electron becomes so big that they don't see any of the defects of the atoms to scatter off in the material, so they can go through without losing any energy. So that's the short quantum mechanical explanation for it. It's actually even more complicated than it sounds, but quantum mechanics allows some materials to go from a normal conductor, just like a normal metal, to become superconducting. Now, what this means is, as we heat a material up, we know its resistance goes up if it behaves like a normal conductor. Semiconductors are a little bit strange, but their resistance never changes or never becomes small anyway. If you take a superconductor, and most superconductors are metals, you'll get to a point where all of a sudden the temperature, known as the critical temperature, will be reached, and the resistivity will drop and eventually go to zero. We call this the critical temperature because this is a temperature where, again, there's no resistance. Electricity will flow. We don't lose any energy. It's really sort of a utopian type material. The problem is the temperatures involved typically are very close to absolute zero. So you save energy by not losing energy to resistance, but you spend a lot of energy, at least up until now, cooling the materials to these low temperatures. Okay, so again, metals, basically if you keep cooling them down to absolute zero, they'll retain some resistance, but never completely lose it all. Superconducting metals, however, keep losing their resistance, and all of a sudden there's a drop-off. After this critical temperature, there's no resistance at all. Superconductors even come into different types. A type 1 superconductor is typically a pure metal. They don't do well with external magnetic fields. Magnetic fields will disrupt their superconductivity. And, the first superconductor discovered, I believe, was lead. Type 2 superconductors are typically alloys, and they hold up much better against magnetic fields, and they also tend to have higher critical temperatures. So the critical temperature depends on obviously what the material is made out of. You can actually depress the critical temperature by putting the material under pressure, and even the crystal structure can be different for these different alloys, affecting the critical temperature. Again, once you drop below the critical temperature, the resistance goes to zero. Here is a chart of all the superconductors, and what's interesting is everything here in yellow is actually superconducting below critical temperature. Now, some of them you got to go really cold, like beryllium. You've got to go down to 0.026 degrees Kelvin before it becomes a superconductor. But some of them aren't all that bad. Tantalum, for instance, at 4.483, I hope I got the right chemical right there, is superconductor. Niobium is superconducting below 9.5, and I think that has the highest critical temperature of all the pure elements. Even uranium and thorium are superconducting, as well as americium, but you wouldn't want a radioactive superconductor, so we don't really use those for that. Lead, superconducting at a fairly high critical temperature, 7.2 degrees Kelvin. Here's some type 2 superconductors. And again, just for reference, we have niobium here, which is 9.26. Now we start using some of these alloys, and barium silicon is 8.07. I can't say silicate because that's silicon and oxygen. Here is carbon, potassium. These are actually buckyballs. So if you know anything about the buckyball structure, these are superconducting. And really, the niobium alloys produce some of the highest type 2 superconductors, where you have this one, niobium germanium at 23.2 degrees Kelvin. And this alloy and niobium tin are oftentimes used in superconducting magnets. Here are some other superconductors. In the 1980s, the yttrium barium copper oxide became a very popular high temperature superconductor because it was actually superconducting above 70 degrees Kelvin, and that's the temperature of liquid nitrogen. These are actually not metals, but rather they're ceramics, and that made them really remarkable. The problem with them is, however, it's tough to make electrical contact to ceramics, so that creates quite a bit of engineering challenge. Unfortunately, the material with the highest superconducting temperature is mercury, barium, calcium, copper oxide, and the mercury, of course, is a toxic metal. So that's not really a great material to be using, but superconducting at 133 degrees Kelvin and below. So again, superconductivity was discovered in 1911 by Ohms. He was able to, I think, detect superconductivity in lead. In 1986, again, these high-temperature superconducting ceramics first appeared, and they reached their highest critical temperatures somewhere around in the late 80s. Currently, the best we can do with superconductivity is about 150 degrees Kelvin, but we're still in search with more materials that display superconductivity at even higher temperatures. Again, what's great is if you can keep these temperatures, these critical temperatures, very high, you don't have to cool down the superconductor very much, and you can send as much energy down the superconductor as possible and not have to worry about losing energy. Right now, superconducting electrical transmission lines don't really make sense. Why? Because the amount of energy you need to cool down the lines is far more expensive than to just use thicker cables of aluminum. Applications, they've been proposed to be used in maglev trains, where you actually use something called the Meissner effect to elevate the train off the tracks. This would reduce friction. Again, very, very expensive because superconducting magnets are expensive. We do use them in MRIs, magnetic resonance imaging, a medical technique. Here we need very powerful magnets. The only way we can reach these magnetic fields and the magnetic field gradients necessary is to use superconducting magnets. Again, eventually we hope to find superconductors that have a critical temperature, close to room temperature, because that way we can transmit electricity without losing any power at all. But as I said before, it costs more energy to cool it down than it's worth it. This is the Meissner effect. This is barium copper, yttrium barium copper oxide, this black right here. And it's been cooled by liquid nitrogen, so it is now a superconductor. This cube right here is actually a magnet. It's a little rare earth magnet. And it's floating in the air because the other property of superconductors is they expel all magnetic fields. With zero resistance, they display something called the Meissner effect, where anytime you try to put a magnetic field near them, they're completely diamagnetic. They completely expel the field, and they'll repel magnets, causing them to float. Again, here's a chart of different critical temperatures. Here's a timeline to where different things were discovered. Hydrogen sulfide at 155 gigapascals is superconductive at 200 degrees Kelvin, but that's not really a practical use there. In terms of other materials, again, these lead alloys, showed the greatest prospect, but unfortunately, again, their toxicity was a problem.